to In the Steam Shop, episode number 3. My name is John, and I'm going to go into a little bit of basics on a few of these episodes on steam engines, steam power. Okay, so in this first episode, we're going to have a little discussion on valves. A lot of my compatriots on YouTube are not using the proper terminology and explanations of how steam valves operate. So to try and explain this a little bit better, go into a little bit of a history and go into the types of steam valves. How do I put this? So what does a steam valve do in a steam engine? Same thing as a valve does in an internal combustion engine. It opens to expel burnt gases, or it opens to let in a new charge of fuel, and closes when you need combustion. Steam engine, though, is not an internal combustion engine. It is an external combustion engine. So the fire or the heat that is needed to operate this engine is external to the device that actually creates the motion, and the motion is the work. So my history has been mostly with steam locomotives, but anything that I've learned from the steam locomotive is easily and quickly changed to other types of steam engines, such as stationary engines, marine engines, logging engines, whatever you want to call the type of engine. Traction engines, it's all the same principles. It comes down to a cylinder with a piston where you admit steam on one side of the piston and exhaust the other side of the piston. When the piston reaches the end of the stroke, you reverse the process and admit steam on the other side of the piston and exhaust it from the first side again, and the piston returns to its initial position. Diagram here is of a very simple engine. It has 4 valves, a piston, and what makes a steam engine amazing as compared to an internal combustion engine is that we are able to put steam, or put the expansive force on both sides of the piston. So in a 2-cycle engine, you will get 1 power stroke for every revolution of the crank. In a steam engine, you actually get 2 power strokes for every revolution of the crank. That was a development of 2 gentlemen, Mr. Watts and Mr. Stephenson, who developed the double-acting steam engine. Although highly inefficient, it was a vast improvement over the first engines that were at that time. Let's put it that way. So I'm kind of swimming here a little bit. So this first picture shows an engine with 4 valves, and like I said, if you take valves 1 and 2 are inlet valves, valves 3 and 4 are exit valves. So you open 1, open 4, close 2 and 3, your piston will go one way. If you reverse that, the piston goes the other way. And then through the means of a crank, you get from linear motion to a rotative motion. And rotating motion was known well before steam engines came along. For example, a windmill or a water wheel. If you could start that rotative motion, you could do amazing things with it. There were sawmills, wind powered and water powered. There was your good old, the reason they call it a mill, your milling stones. You could mill your grain. They even figured out how to power looms to make your cloth from a water wheel or a windmill. All these things, woodworking shops with all kinds of machinery in it, wind driven or water driven. This was all available. It was when they had the idea in the very late 1700s and into the early 1800s of utilizing steam pressure to drive machinery. I'm diverging from what I was talking about again. So let's get back. We're going to show you a little bit more about the theory and design of the simplest valve that was used in steam engine, developed by Mr. Watts, and figured out how to operate it and get it to reverse by Mr. Stephenson. So we're going to look at the second picture, which is a drawing of, actually there's two pictures here, and it shows the valve. It's a block with a hollowed area in the center, and the valve face, which is on the steam engine, on the cylinder itself. And by moving that valve back and forth, and this valve in particular, to the slide valve, is called an outside steam valve. We're going to go to another picture here. I'm going to point it out for myself on the screen, and you can follow along. In this picture, you can see that the steam enters at the top and surrounds the valve. The pressure of the steam is what seals the valve to the valve face. Now, as the valve moves in one direction, it opens a port that allows steam to enter the one side of the piston, and by sliding over, it opens a port on the bottom that allows the steam to exhaust through the bottom of the valve and out of the engine. And by controlling that little valve rod back and forth, that's how they control the motion. In the next picture is a little bit better of a diagram of the arrangement of the valve. And the amazing thing is the numbers that are involved in designing this are very simple. If you take the three slots that are in the engine, and in this drawing they are F, H, and G, okay, and assign those a value, whatever it is, the distance you want your eccentric to move that. So F, H, and G, let's give it a value, just as a mathematical genius that I'm not, of X. That sets, so there's three slots with a value of X, and then there are two spots in the middle, I. Let's give those also a value of X. So you've got one, F is X, I is X, H is X, I again is X, and G is X. There's 5 X units, 5 units, whatever they might be. Okay? So those 5 units will determine the size of the valve itself. The valve itself needs to be in width 5 times X plus a very tiny fraction. The distance that's shown as J is 3 times X. All right, So when the valve is in the position it's shown in now, it shows F, I, and H are uncovered. So this is the exhaust side now. And that G is open, admitting steam from around the valve into the one side of the piston. You reverse that position of that slide valve, and now the piston will reverse. That's as simple as these things are. Now, why was it even into the 1940s on steam, on the Liberty ships? You look at the winch engines that they had on board those ships, and you see that it's an outside steam valve. Why was this so popular even so late into the time? Because it is an easy engine to replicate the parts with a simple machine shop. Sometimes not so simple. You would need a milling machine, for sure, but you didn't need to have a massive, huge milling machine. You just needed the materials on board. If a valve broke, you could replace it. If a seal broke in these systems, the seal on a steam chest, which is the entire apparatus around the steam face, and it's a separate piece, if that seal broke, it was just a matter of replacing soft metal, such as copper, into that, replacing it very easily. You didn't need to have a warehouse full of replacement parts available to you. You just needed a bunch of basic steel. That's why this was so popular. Easy to maintain in situations where all you had was a small machine shop or a small facility. You could keep these engines running. Later on, with the development of electric motors and stuff like that, and hydraulic systems, you still only needed a few parts that you could fix anything on board the ship, or on the trains and on all the rest of it. But in those days, you didn't have a major supplier of parts just around the corner from you. You had to build your own parts. And that's why these engines were like this. So this is the outside steam valve, the piston valve, the arrangement, whether you see it as a steam engine drawing as I have it here, or whether it's a marine engine. This is your simplest one. A gentleman by the name of Mr. Crispin is building a nice little locomotive. He's got piston valves. That's the next generation and improvement on this. This simple system was in most engines right up until this end of steam. So that's valves. Let's see if I can turn around and edit this into an understandable program, because I have been rambling on for too long.